Hello. I will be talking about Gaussian. So Gaussian is a computational chemistry software package which can perform several quantum mechanical methods, including ab initio, semi-empirical, and density functional theory calculations. These calculations slash methods are based on quantum mechanics and usually by solving the Schrodinger's equation or using approximations to determine the nature of atoms and molecules. It can also perform calculations using molecular mechanics and molecular dynamics, which are more based on applying classical mechanics to molecular systems to observe their motion. Um, those two methods cannot be used to look at bond breaking and bond forming, but essentially all these methods can be combined to model structures, predict properties, optimize geometries and energies in order to simulate reactions and predict favored mechanisms. So it's very useful for looking at all the aspects of a reaction, including the structures in different stages of the reaction, as well as predicting what reactions will be favored. Gaussian is especially useful for computing catalyzed reactions, which I will talk about later. Uh, and for the operations, XYZ files, which we have discussed in class, that contain the information of the position of atoms in space, are converted into Gaussian input files known as .com files. And then using these files, Gaussian can perform several types of calculations using the quantum mechanical methods, including ground state optimizations, transition state optimizations, property optimizations, single point energy calculations, and intrinsic reaction coordinate calculations. So geometry optimizations are similar to or what we've done in class before with optimizing the structure of some simple molecules and vanillin, where basically the calculations are to find the lowest energy structure, and the vibrational frequency is used to find this lowest energy. And then with transition state optimizations, the computation involves calculating a saddle point in the potential energy surface, which is essentially like being at the top of a hill in that surface. Then with property optimization, bond lengths, angles, and or dihedral angles can be constrained or adjusted to certain parameters in order to more closely observe how a molecule's energy changes over a desired reaction mechanism. And this is useful for the process of finding transition states as well as some other molecular systems. And then for single point energy calculations, the calculation is done at a specific point in the potential energy surface without modifying the geometry. So it is essentially a more specific form of the previous optimizations. And then with the intrinsic reaction coordinate calculation, the path along the reaction coordinate is calculated using the gradient of the potential energy surface, starting from a transition state. So essentially, starting from a transition state, uh, the Gaussian can calculate using the gradient how to get down from that top of the hill of the reaction coordinate and fall down to ground states that are potentially intermediates or products and reactants in the desired reaction. So these different jobs are outputted as log.log files that contain information about the energy and vibrational frequency of the molecule, including values to find the enthalpy, entropy, and Gibbs free energy. So it's a little hard to see in right here in the pictures, but on the left there are several files, .log files, .com files, which are all for the same molecule, but with Gaussian, several jobs can be done at once using high performance computing clusters. And then on the right is the outputs of the many energies, including the values to find the enthalpy, entropy, and Gibbs free energy. So this is an example of Gaussian in use. So in my research project, actually, right now with Dr. Agba, the overall reaction that I'm looking at is this one right here, where basically a sulfate amide and a silicon amine, or sorry, let me correct myself, the sulfur fluoride compound on the left, as well as the silicon amide on the left also, the two reactants and a calcium catalyst are used to form this sulfan amide product on the right. So one of the proposed steps for this reaction is right there. This is the calcium complex with DAPCO, which is a nitrogen compound, and the sulfur fluoride basically exchange. So then the sulfur gains nitrogen compound called DAPCO, and then the calcium complex coordinates with the fluorine. So using ground state optimization for the reactants and the products which are in the above reaction / intermediates, the energy of each molecule was computed, and then the energy of the transition state of this step right here, the proposed step, was also computed. So, and then using those energies, we can find the energy difference of the transition state relative to the calcium catalyst. And essentially, what this does is it allows us to make a reaction coordinate for this proposed step. So as you can see, we start with the products on the left at zero value for energy, kilocalories per mole, and then it goes all the way up the top to 45.3, which is the transition state energy, and then on the right, very right, is the product or intermediate that's at 17.3 kilocalories per mole. And then using these methods, it's also possible to find possible intermediates in between the products and reactants, which are those numbers in the middle, 12.4 and 19.0. Those are ground state energies of intermediates in this specific step of the reaction. Then Gaussian also has a visualization tool called GaussView, which, as you can see there, you could see it was moving in the direction of like the bonds breaking and forming. So this is called GaussView, and it uses the XYZ files to show the vibrations of the molecules. So you can basically visualize how a transition state is occurring, how the bonds are breaking, how they're forming, which gives more insight into how we can expect the reaction to look like, the mechanism to work. So in the real world, there are several, including the previous example that I've shown. Determining energies and favored pathways for reaction is a very useful very useful using Gaussian, and then predicting the efficiency of catalysts for reactions involved in fuel production is another application of Gaussian, as well as predicting the best reaction for forming compounds used in drug development. This is the example that I used previously, where we're optimizing a reaction predicting the most favored pathway to form these sulfonamides, which are used in certain drugs. And then Gaussian can perform molecular dynamics to find binding energy calculations to understand drug binding interactions and drug delivery. And also, predicting reactions can help us predict what experiments would be best to run, so that there is so we don't necessarily have to run more costly experiments that are also potentially environmentally costly or harmful. It gives more insight into what we can predict. Thank you very much.